Hello and welcome to Chapter 30, where we talk about light emission, or the emission and absorption of light and how light interacts with matter. The fundamental thing that we're going to be talking about when we're talking about light is excitation, where we have these energy levels which are quantized, meaning that there are only certain amounts of energy levels. So when an energy is introduced into an atom or some other form of matter, it can jump, cause the electron to jump or the matter to jump in energy levels from one energy level to another, equal to the amount of energy that's put in. It then emits that photon, which is a light particle, as it goes back down to its initial energy state. So this is conservation of energy, where you have to have a certain amount of energy between particles or between the energy levels, and then this photon emission is only going to be allowed for the certain amounts of energy differences between the first or the second or the third quantized energy levels. Just as each electrically neutral element has its own number of electrons, each element also has its own characteristic set of energy levels. Electrons dropping from higher to lower energy levels in an excited atom emit with each jump a throbbing pulse of electromagnetic radiation called a photon, the frequency of which is related to the energy transition of the jump. We think of this photon as a localized corpuscle of pure energy, a particle of light that is ejected from the atom. The frequency of the photon is directly proportional to its energy. In shorthand notation, E equals H times F, or energy is equal to Planck's constant, which is a constant which converts units times the frequency of the electromagnetic radiation or the electromagnetic photon that is released. If you take a source of light where the atoms or the matter is excited in some way and emits light of certain frequencies, then what you're going to see when you pass it through a couple of lenses and a prism is that because of the angles and the difference in indices of refraction for different wavelengths of light, these different wavelengths of light are going to be reflected onto a screen or a detector at different points. Where these What these points are going to correspond to different wavelengths, and from there you are able to find the quantized emission spectrum. This is called spectroscopy. When you look at an incandescent bulb, it's going to be powered by black body radiation, or is going to have an emission spectrum that's dealt with black body radiation. If you'll remember the emission spectrum that we were looking at several weeks ago, then you'll remember that while there were different colors that were more or less intense for black body radiation, and that frequency of the peak was proportional to the temperature, what the emission overall was not quantized, which means that it would go over the entire electromagnetic spectrum. However, if you have light that's dependent on the energy levels of an atom, then what you're going to see is quantized frequencies of light or quantized wavelengths or energies of light that are coming out of the stimulated atom and just making these strong bands of light for each given frequency, for each given energy level, or difference in energy levels, rather. When we view white light from an incandescent source with a spectroscope, where incandescent refers to black body radiation, we see a continuous spectrum over the whole rainbow of colors. If a gas is placed between the source and the spectroscope, however, careful inspection will show that the spectrum is not quite continuous. This is an absorption spectrum, and there are dark lines distributed throughout this. These dark lines against a rainbow colored background are like emission lines in reverse. They are absorption lines. Atoms absorb light as well as emit light. An atom will most strongly absorb light that has the frequencies to which it is tuned, some of the same frequencies it emits. When a beam of white light passes through a gas, the atoms of the gas absorb light of selected frequencies from the beam. The absorbed light is re-radiated, but in all directions instead of only from the direction of the incident beam. When the light remains in the beam spread out into a spectrum, the frequencies that were absorbed appear as dark lines in the otherwise continuous spectrum. The position of these dark lines correspond exactly to the positions of lines in an emission spectrum of the same gas. On the left, you see white light pass through sodium vapors. These sodium vapors are going to absorb and then re-emit in random directions, so not going straight along the line like the white light is. Certain frequencies of light, which are corresponding to the difference between energy levels. These is going to be an absorption spectrum. So when you look at the right side, when you look at all of the light that isn't showing up in your spectroscope, what you are going to see is going to be light that has these certain frequencies that were absorbed and then re-emitted so that they're not going straight through the lenses anymore, and you don't see them popping up as much in the spectroscope. These are absorption lines. However, if you were to just emit, to cause the sodium vapor to just emit light at its given energies, it would be at the same light emitted as would be absorbed by the sodium vapor under the white light. Many materials that are excited by ultraviolet light emit visible light upon de-excitation. The action of these materials is called fluorescence. In these materials, a photon of ultraviolet light excites the atom, boosting an electron to a higher energy state. In this upward quantum jump, the atom is likely to leapfrog over several intermediate energy states. So when the atom de-excites, it may make smaller jumps emitting photons with less energy, as you can see here. So you have the ultraviolet light, which would excite you from the ground level up into the second, third, fourth level of energy. So you have these quantized energy states, which are the steps here. However, as it de-excites, it might not skip the steps the same way that the ultraviolet or high energy light would. This means that it would emit lower frequency light, which is lower in energy but is in the visible spectrum and is visible to us. This is what is meant by fluorescence. When excited, certain crystals as well as some large organic molecules remain in a state of excitation for a prolonged period of time. Unlike what occurs in fluorescent materials, their electrons are boosted into higher energy levels and become stuck. As a result, there is a time delay between the processes of excitation and de-excitation. Materials that exhibit this peculiar property are said to have phosphorescence. The element phosphorus is used in a variety of luminous materials, even toothbrushes that are made to glow in the dark. Atoms or molecules in these materials are excited by instant visible light rather than de-exciting immediately, as fluorescent materials do. Many of the atoms remain in a metastable state, a prolonged state of excitation, sometimes for as long as several hours, although most de-excite rather quickly. If the source of excitation is removed, for instance, if the lights are put out, an afterglow remains while millions of atoms spontaneously undergo gradual de-excitation. The afterglow of some phosphorescent light switches in the home may last for more than an hour. Now that we kind of understand the process of excitation and de-excitation, which gives way to light emission from atoms, we're going to talk about a few types of lamps and diodes. So the common incandescent lamp consists of a glass enclosure with a filament of tungsten wire inside through which an electric current is passed. So that is just blackbody radiation. That is just heating up a material and then having white light come out of it. The common fluorescent lamp, in contrast, consists of a cylindrical glass tube with electrodes at each end. In the lamp, as in the tube of a neon sign, electrons are boiled from each of the electrodes and forced to vibrate to and fro at high speeds within the tube by the AC voltage. The tube is filled with very low pressure mercury vapor added to argons. Mercury atoms are excited by the impact of the high-speed electrons, much of the emitted light in the ultraviolet region. This is the primary excitation process. The secondary processes occur when the ultraviolet light strikes phosphors, powdery materials on the inner surface of the tube. The phosphors are excited by the absorption of the ultraviolet photons and fluoresce, emitting a multitude of lower frequency photons that combine to produce white light. Different phosphors can be used to produce different colors or textures of light. What we see nowadays, mostly in TVs and electronics, is something called light emitting diodes, which you'll remember from our discussion of the AC-DC converter. A diode is something that only passes through current in a certain direction. So, in one common LED design, a layer of semiconductor that contains free electrons is deposited into the surface of another semiconductor that contains energy holes that can accept these free electrons. An electrical barrier at the boundary of these two materials blocks the flow of electrons, but when an external voltage is applied, the barrier is overcome and energetic electrons cross over and drop into the holes. In a way similar to de-excitation, dropped electrons lose potential energy that's converted into quanta of light, photons, just as a bowling ball rolling off a table makes a loud kerplunk when it hits the floors. The analogous kerplunk of electrons in an LED is the emission of light. The drop in electron energy is converted to light. Finally, we are going to talk about coherent light and lasers, where laser stands for light amplification by stimulated emission of radiation. Light emitted by a common lamp is incoherent, as photons of many frequencies and in many phases of vibration are emitted. The light is as incoherent as the footsteps on an auditorium floor when a mob of people are chaotically rushing about. Incoherent light is chaotic. A beam of incoherent light spreads out after a short distance, becoming wider and wider and less intense with increased distance. Even if the beam is filtered so that it consists of single frequency waves, monochromatic light is still incoherent because the waves are out of phase with each other. A beam of photons that have the same frequency, phase, and direction, that is, a beam of photons that are identical copies of each other, is said to be coherent. A laser emits a beam of coherent light that spreads and weakens very little. Using the metaphor of incoherent light as a bunch of people stomping around in an auditorium with no rhyme or reason, a laser or a coherent light would be people marching in step at the same frequency, in the same direction, and at the same time. This is said to be the defining property of lasers. So you can get monochromatic light by stimulating a matter to only emit certain frequencies, as is the case with the LED. But the laser is about the only thing that I can think of that emits coherent light. The way a gas laser works, and there are also solid state lasers, which are a little more physically and conceptually complicated, is having a gas tube filled with particles or gases or matter that can be stimulated. This can be stimulation, as was the case in the earliest lasers, by just applying a very high voltage across the tube. This stimulation is going to cause the electrons in the gas to go up to higher energy states and then release the same amount of energy or the same amount of the same frequency of light, all of them together. And then this is going to create a monochromatic light that's going to go through the tube. This monochromatic light would then stimulate other gases in order to cause them to also raise and emit light. And that light is going to stimulate the other parts of the gas. And what actually happens with the gas laser is you go to the edge and there is a mirror and it reflects back and forth and it creates this feedback loop where the light is going to stimulate more and more of the material of the gas to release more and more light. This is all going to be coherent light as well. So some of the light that comes out is going to pass through the mirror, and that is going to be our laser beam. So it's coherent light that is stimulated by an outside energy, causes there to be more stimulation when it runs into other atoms and is passed back and forth within the tube until it is released. Typically, this is not a very efficient process, and you'll have to have very high power for not very high power output of a laser. When I did this in undergrad, I think I had to have a 5 or 10 kilovolt power source in order to stimulate a gas laser, which would output power in milliwatts. So typically, kilovolts are units of energy and milliwatts are units of power, but typically the efficiency of a laser is less than about a few percent. So it's typically about 1%. The uses of lasers are that lasers have found wide use in surgery. Lasers are also used in cutting and welding procedures, mainly where small parts are involved. They cut cleanly. Laser beams weld wires into microcircuits and repair damaged wires inside glass tubes. They are used in reading CDs and DVDs, and they create holograms. One day they may trigger controlled fusion power. A huge application is in communications, whereas radio wavelengths span hundreds of meters and television wavelengths span many centimeters. Wavelengths of laser light are measured in millions of a centimeter. Correspondingly, laser light frequencies are vastly greater than radio or television frequencies. As a result, laser light can transmit an enormous number of messages bunched into a very narrow band of frequencies. Communication can be carried in a laser beam directly through space, through the atmosphere, or through optical fibers, light pipes that can be bent like cables. The laser is at work at supermarket checkout counters where code reading machines scan the universal product code symbol printed on packages and on the back cover of this book. I'm using the Kindle edition, so that's not the case for me. But laser light is reflected from the bars and spaces and converted to a electric signal as the symbol is scanned. The signal rises to a high value where reflected from a bright space and falls to a low value when reflected from a dark ball. The information of the thickness and spacing of the bars is digitized and processed by a computer. Environmental scientists use lasers to measure and detect pollutants in exhaust gases. Different gases absorb light and characteristic wavelengths leave their fingerprints on a reflected beam of laser light. The specific wavelength and amount of light absorbed are analyzed by a computer, which produces immediate tabulation of the pollutants. Lasers have ushered in a whole new technology, the promise of which we continually chat tap. The future for laser applications seems unlimited.